This afternoon we're going to have a very exciting lectures given by Professor Karl Johansson. Johansson or Johansson?
Johansson.
Yeah. Actually, whatever I pronounce, he always say yes. So I'm a little bit confused. It depends on use American pronunciation, British, Danish, or Swedish. Yeah. So anyway, Professor is associate with KTH, actually Royal Institute of Technology in Swedish colon. Kungliga Tekniska Högskolan.
Excellent. Excellent.
Thank you. Yeah. So he in that university, he has two positions. One is a professor in the School of Electrical Engineering and Computer Science, and also he's the director of the Stockholm Strategy Research Area in ICT, the next generation, right? And I think he receives master's degree and PhD degree in another very famous Swedish university, Lund University. I think it started from mid-ages, 15th century. Yeah, it's a very famous, nice university in the world. And ever since he had been a visiting position in various universities like UC Berkeley, Caltech. I'm very familiar with that. And also next one is NTU, I don't know, NTU in Taiwan and in Singapore. Singapore, okay. And also the Hong Kong UST, IAS, and also in National Taiwan Normal University, right? It's NTNU, right? Norwegian. Where is it?
Norway.
Norway. Okay. Yeah. This is a lot of university in the world have the same abbreviation, so I had to say where that is. Yeah. Okay. And then his research covered the network control system, cyber physical system, and the application in the transportation, energy, automation, and something like that related to today's talk. And he is the member of IEEE Control System Society Board of Governance, and also the executive board in IFAC, I think this is International Federation of Automatic Control, right? Okay. And also the European Control Association Council, yeah, all very important position. And he has received several Best Paper Award and other distinguished scholarships. And he's a distinguished professor with the Swedish Research Council and Wallenberg Scholar. He has received a Future Research Leader Award from the Swedish Foundation Strategic Research and the, I think this Triennial Young Author Prize, okay? And from IFAC, International Federation of Automatic Control. And he is also the fellow of IEEE and the fellow of Royal Swedish Academy of Science and Engineering, and also IEEE Distinguished Lecture. Right. So has very, very impressive, respected bibliography. And today he's going to give us a talk on cooperative road transport, opportunity and challenge in network control. So let's give a big hand to Professor Johansson. Yeah.
Thank you. Thank you. When I got this invitation, it was a bit challenge for me what to speak about in front of this distinguished audience. I decided to talk about one project that I have been involved with quite some years. I've been collaborating with Swedish industry here for about 15 years. It started small. I had a student supported by this company and so on, and now it's grown really to quite some activity. So I will tell a little bit that story, but I won't tell it in a chronological order. I will formulate it coming from a scientific problem that I'm interested in solving. And so with that, you will see that it involves a lot of activity by people in my group. Most of these are former members, students or postdocs and so, and most of them have moved on to industry or faculty positions. So what's the problem that I'm interested in solving? It's a very practical problem that our society is solving every day. And that is, how do we transport goods around in society? So, and society in this case is Germany, because they have a nice road network represented by a nice graph, as I put up here. And of course, most goods that we transport around, we transport between the major cities, because that's where industry is and that's where people live. Right? What can we say about this transport problem? We can say a few things. I mean, transport is mainly on road. And how large are we talking about this transportation? So in Europe, we have about 2 million these long haulage heavy trucks moving around. This that goes around between cities. Germany, for instance, one is 20% of those. I didn't find the figures for China, but if you sum up all trucks in China, it's 19 million. So perhaps you can split this with 3 or something like that. So you see that the number of vehicles that we have, it's not enormous, but it's big, right? That are the carriage. What can we say more about this system? Yeah, basically, since it's about moving things around with a certain purpose, it's like a distributed control system, right? But there is actually no coordination today. What do? It's very low tech. You give a piece of paper to a driver, and the driver is now supposed to drive a load from one point to another point, which is maybe a day away. And that's how it works. It's also have some other characteristics which are quite interesting when we want to formulate this now as a scientific problem and solve it. And of course, there is a lot of constraints and objectives and so on, but I will try to simplify the story to start with. So the problem I'm interested in is if we compare to what's being done today, can we do this in a more efficient way by not changing completely how we are driving around over this network, but adding cooperation in a systematic way? And what you will see is that cooperation will mean that trucks are traveling together in vehicle platoon, but also other type of cooperation. So that's the problem that I'm interested to understand. How much could we do on that? And what could we say? How can we motivate this problem? So what's the characteristics? If we start from a societal viewpoint, what we first of all can say is that this costs a lot of energy in society. Transport, as you know, on broad scale, we can say it's 1/3 of all energy we are spending in the world go to transport. And freight transport on roads is a dominating type of transport when we look at surface transport. It's interesting compare. It's a little bit small here, but if you look in this on these histograms here, it's the distribution between inland on waterways, road and rail. And you see, if we compare in the OECD and in EU, we see that roads are dominating. China is actually, surprisingly, at least to me, has surprisingly much water. I don't know if that is going to stay or not. But we can see that road transport is really a large part of this. And this road transport is, of course, today polluting a lot. From an engineering viewpoint, what is interesting is that this is very inefficient. So these figures are now from one truck manufacturer, Scania. So what you see there is 1/4 of all these trucks runs completely empty. And the average load capacity is just a little bit above 50%. So for any system that you would have, right, you would say that this is waste. But of course, one reason why it's waste is that there is not so much information that is being communicating in this system. So that's one motivation. Then if you should target this problem now, what should you focus on? So this pie chart shows the life cycle cost of a fleet owner. And what you see there is that 1/3 of the cost is fuel. The other big chunk there is driver. So 1/3 is driver salaries. So you see that if you should target something, you should try to make it more fuel efficient, and you should try to automate it. And then you will target a large piece of this cost. And how we are going to do that? Yeah, what we are going to do is what we all know, right, from technology. We don't have to go into detail on technology, right? Today we have real-time traffic information. Our vehicles is quite sophisticated piece of equipment with a PC on board, all type of sensors, radar, and so on. We have different types of propulsion being developed now. Electricity, for instance, like this Swedish electric highway, or batteries maybe in the future. And what I'm going to talk about here, platooning and automated driving that is coming in. So with this type of technology, we can develop a system. And let me show the system that we have in place today. So it's a very simple principle. So we take now 4 cities in Germany, and we say that there are 2 transportation missions going on between these cities. And they happen to overlap in time and space, a little bit there in the middle. So if they do that, what we can do is now that we can allow these 2 vehicles to go together in a platoon like this. And if they do that, they will save some energy. If we now would know all the different transport missions going on over Europe, right? We can try to do matchmaking automatically. And the system on a low level now, which is in place, looks like this. So this is our trucks that are now running automatically. So the truck in front is communicating position, velocity, and braking to the vehicle behind. And then that is then regulating automatically the distance to the vehicle ahead so that we get a minimized air drag. As you see in this experiment, there are drivers here, but they are basically not doing anything there. When you can do that you can go with the platoon in steady state, of course you need to do other things because we want to form this on the road. We need to be able to form platoon automatically, like you see here. And also what we need to do is to be able to handle traffic. So a situation that can happen is like what you see coming up here, that there is a little white car. That human driver, for some reason, wants to sneak into that platoon. And then, of course, now these automatically driven vehicles need to detect that vehicle and open up, as you saw, maybe communicate with the driver saying that this is okay, now I split a little bit. And then when the human decides to leave again, you merge and so on. So you can see that on one level up, so to say, from just being in steady state to driving, you need to be able to handle this type of situations with the traffic around. And of course, with the traffic or other incidents, it could be that you need to emergency brake and so on. So this needs to be, yes, Ling?
Is that random or planned?
The braking here.
No, the vehicle.
No, I mean, in here, this test track is actually a test track in Barcelona where we run some experiments. And everyone who is driving on that test track had to be a professional driver. So these are really like, racer drivers.
So, I mean, the white car, the small white car.
Yeah. This is also, because, if something goes wrong, I mean, this is nice, right? The system works, that you see. But of course, when you do this test, if something doesn't work, you want to have a really good driver there so you don't smash someone in between. But you will see that we have a lot of experiments also out on real roads and so on. But this happens to be in Barcelona test.
Sorry, this may be a question should be said earlier, but since somebody already asked, how does this system compare to Peloton, a startup company in the
Yes. I was actually, a year ago, I was standing in there in Peloton and give a little bit a similar talk. Yeah, Peloton. Let's come back to Peloton a little bit later. But you can say that they do a small version of what I'm going to talk about here. So they try to commercialize platooning between 2 vehicles and focusing on that part, 2 identical vehicles and so on. What you will see here is that we will talk about a little bit a bigger perspective than that. But it's a very relevant company, an interesting company as well. I will come back also talking to what other industries are doing. So you can say that basically all major truck manufacturers today are investing in this. So it's a big area now. So the picture I want you to have now is to think about that in the future we will have a situation like in my cartoon here. So you see that we still have transportations from ports to cities to industries and so on. The difference is now that they will go in platoons, and they will form these platoons on the road. So we could describe this as in many cases when we look at control of complex system in a hierarchical way, right? So what I talk about here is that on a lower level, we have the vehicles and we have the platoons. One level up, we have something which I call cooperation. With that I mean that we need to be able to interact with the other vehicles out on the road so that we can form these platoons that you saw on large scale. And further one level up, we have something here which I call a fleet layer. So this now gives possibilities so that you have two different fleet owners, those who have 10 or 20 trucks each. They could collaborate now. Of course, today you don't collaborate because you don't want to give up your customers and so on. But if you, so to say, construct a market out of this, you can open up a completely new type of business. So that cooperation could be done on the fleet layer, and typically the big ones have something like you see here down to the right, namely some people who are working in a back office. Maybe you have something in Stockholm if you have operation over Europe where you follow all the trucks and so on, a little bit like a air traffic management things. So in my talk here today, I will describe a little bit what from bottom up here, from the platooning to the formation to the fleet coordination. And I thought since there are a few students also around, what I will do is that I will talk about some open problems, something that maybe we just started working on, and then there will be some problems which I think we have solved. So there will be a mix here, and thanks for the questions. For me, at least, it's perfectly fine if you want to interrupt and ask more questions as we go along. Otherwise, let's start with vehicle platooning here. So control of vehicles, if you are in the control area, this has been studied for a long, long time. More than 50 years ago, there was this paper coming out of MIT. Bill Levine and Mike Athens wrote a paper about that actually we can control a platoon of vehicle as a string of masses. And then they developed some theory and so on around that. And the biggest success so far when it comes to platooning is probably this project in California, the PATH project on the automated highway, where they demonstrate outside San Diego in '97 that they could actually control a string of vehicles going close together. And they also describe of how the whole system could be automated and so on. So since then, a lot of things have happened, and particularly the last 10, 15 years or so. And that's what I'm going to talk about. And in Sweden, I'm happy that we have two commercial truck manufacturers. We have Volvo and on the west coast, and then we have Scania on the east coast. And both of them have been early adopters of this technology, and we have projects with both of them. Of course, they are our fierce competitors, so they don't give up any ideas to the other or so. Okay, but let's first go back to physics now. So why do we do platooning with trucks? It's very simple. So here you see a CFD simulation. So the color indicates the air pressure. And you see that when it's sufficient distance between the two vehicles, the air pressure they experience is about the same. While when we are moving closer, you see that the air pressure is being reduced significantly. So thanks to this, so if we are moving now the distance between the vehicle, we make that smaller and smaller. You see on the x-axis here, where you have the distance 10, 20 meter. At that point, the air drag reduction, as you have on the y-axis, can be down to or up to like 40-50%. So 40-50% air drag reduction is very much. And it means that you can get the fuel reduction for driving this truck, which is something between up to 20% actually. 5 to 20%. Why that range is so big is that depends a lot on the experimental condition and so. So nominally when we run, it's typically 10%. And if we are now talking about 10% of the fuel can be reduced of something that maybe consumes 10-15% of all the fuel that we are spending or all the energy that we spend. You can imagine that this is an enormous big figure even if it's just a few percent. So of course, this we cannot do if we are not automatically driving the trucks. So you see that we get this benefit when we are 20 meters or so. So we want to be that close, but we cannot expect that a manual driver will be able to drive that close, right? So we need to do that automatically. So let's go into detail now on how do we control the individual vehicles in this platoon. And to start with, let's go back to a single vehicle. How do we automatically control the velocity of a single vehicle? So this is not as simple as just keeping constant velocity as it used to be. Instead, what we do, yeah.
In the previous graph, you showed that when the relative distance is large, then the air drag, reduction goes
Exactly.
down. Okay,
Yeah.
negative of negative.
Yeah.
Okay, right.
Notice also here that I have 70 meters here. So if you continue, so even if you drive 100 legally in many countries, if you drive like 100 meter, you would experience some air drag reduction. So you don't have to be that close. You can experience benefits, and this you will see. Truck drivers typically know that, and they drive with a certain distance close just to reduce energy. Yeah, thanks for that clarification. So what you do when you want to regulate now the velocity is that you solve online an optimal control problem. It's not a very advanced optimal control problem. You can go back to the classics, right? So you formulate the fuel consumption for a vehicle now that, for instance, should traverse a hill which have some slope of alpha there. So you formulate then the cost function, the fuel. So how much fuel does it cost? So you get an expression like this. You integrate over an horizon, which is typically a couple of kilometers that maybe covers that hill. And then you write out Newton's equation. So you get an optimal control problem which you can solve. And when you solve this, you get solutions which are very intuitive. So what you see down here is that we have an uphill. So this is altitude going up and the altitude going down. And in the bottom plot, you see the velocity. So if you have a light truck now, like the blue one, you see that you should just keep constant velocity. So if you don't have to, you shouldn't change the velocity. It's always best to go with constant velocity. But if you have a heavy truck now, the optimal thing to do, as you see here, is to speed up a little bit before the hill. And then you let the velocity go down and vice versa, or the opposite in the other direction. So this is optimizing the fuel and reduce the fuel a little bit. So this suggests how is the optimal velocity. And this now you can implement just into the controller that keeps the velocity. Of course, this has assumed that you know the road grade, which I will come back to how we'll get that. So that is the control mechanism that we have in place today. So let's now look at the control architecture inside the vehicle. So here you see the control system. So from the left there, we have the sensor information input. So we have data, for instance, from other vehicles, their position and so on. We know our own position. That goes into the controllers, which are the different cruise controllers here in the middle. And then we actuate over here. So I talked already about the energy management system. That is where we send the reference velocity. But of course, we also need to control the braking. So the braking management system and the gears, the gear management system. So this is basically the control that we have. I put this slide here just to emphasize that notice that now when we do something more advanced, like the CACC, which is the Collaborative Adaptive Cruise Controller, which is now the platooning, I don't change basically anything in the vehicle. I only change a piece of software that sits here. Another thing is that who have control of that switch. So that switch the driver has control of. So we don't at this point take over completely from the driver. The driver can always decide what he wants to do. If he accepts that we go in a platoon, then we run a system which would just look like that, right? What you would expect. Where vehicles are exchanging information either via their radar, so they measure information, measure their distance to the vehicle in front, or via the wireless communication. Either Wi-Fi, vehicle to vehicle, or vehicle to infrastructure, and infrastructure back to vehicle. So let's go in a little bit into detail on how the control is now being done on the lowest level. So what I said was that it's important to be close, right? So we want to regulate the distance between the trucks. And it's obvious if we have a long string of vehicles now that we would like that to be distributed. Maybe each vehicle would like to just control based on the information from the vehicle ahead and so on. And that problem, as I said, has been studied for a long time, and it's well known that what we can get is something called string instability. What that means is that the disturbance in the first vehicle could propagate and increase as we go down the string, as you see here. And that we want to avoid, and there have been different studies on when we can avoid that and so on. So what is important in this most of these studies are theoretical. The experimental studies has been in quite ideal situation. We, some years ago, did some experiments where we actually tried a similar type of structure that we developed. And then we are now, here is Stockholm up there, and we are west of Stockholm. So it's a highway which is 45 kilometers. And we went back and forth there with these platoons over and over again. And the graph that you see there is altitude. So it's a little bit hilly here and there. And so. So after these experiments now, we looked at data. And yeah, again, you see the control architecture was that simple, what I said, distributed one, right? So each vehicle controls its own velocity, and then it communicates to the controller behind. And this is what we achieved. So in the top plot here, you see now a segment, just a few kilometers. So it's an uphill, downhill, and so on. The second plot shows the velocity. The third is the distance between the vehicle. Here you see the torque generated in the two first vehicles, and that's the braking of the second vehicle. And as all of you who have a background in control or vehicles see that this is bad, right? You see the second vehicle, the red one now, when we are going downhill there, you see that the velocity oscillates. The first vehicle, the blue one, is doing something you would expect, right? The speed takes up because you're going downhill, so you go. The second vehicle should just follow that vehicle, right? So it should have constant, but it's not. It's oscillations there. We see here that the distance is oscillating, so the distance between. And you see even so that the second vehicle has to brake. And we talk about saving fuel. So the worst thing you can do is that you brake, because that means that you are losing fuel, right? So when we got this, and my student who graduated 2014, he did this experiment some year earlier. When he got this result, we didn't look there first. He just looked at the data of how much fuel you will save over these 3 weeks of platooning. And the total amount of fuel that you saved was something negative. So he came back to his advisor to me and said, I cannot defend my thesis on platooning now because I've shown that you spend more fuel with platooning. But that was, as with many good PhD theses, that was an encouragement to start a new PhD. So because we went in and started to look at data, and that's when we found that there were a few segments like this where the controller was doing bad. And then we thought that maybe we shouldn't trust this control architecture in the literature. Maybe we should think a little bit about that. 2 important things here. So one thing is that topography variation, the hills. Maybe that plays a very important role that we haven't thought about before. And another thing is, how should we regulate the distance between the vehicle? Maybe we shouldn't regulate the distance. Maybe we should regulate something else. And I'm going to show a little bit what that means and our new controller that we come up with. So let's do a simple thought experiment just to see our idea before we come to some mathematics here. So let's say that we are driving on a flat road and then we come to an uphill. So we will never know perfectly where that uphill is, right? We always have some uncertainty. Let's say that you want to keep a constant velocity. Then what this vehicle is going to experience is a little bit a dip in the velocity there, exactly where it hits the uphill. So that I can plot now like to the left there over time, or I can plot it over space along the road, right? And for a single vehicle, there is no difference. It will just look the same. Now what I do is that I put a platoon there, and I say that the second vehicle can perfectly control its distance to be d to the first vehicle. And the third vehicle can also perfectly control its distance to the vehicle ahead. So perfect control here. What is going to happen? So when the disturbance of the road hit the first vehicle, all the other vehicles are going to experience the same disturbance, right? Because we have the same perfect control. While if we now look at what is happening in space, the disturbance is going to hit in different instances in space, right? And now if you animate this picture forward, what is next going to happen is that the second vehicle is going to experience the same uphill, right? So that gets the same disturbance twice, and then for the third. So you see that there is something that could happen, which is some sort of a propagation of that type of disturbances that we didn't take into account in the controller that I showed you. Then we can regulate on other. We can regulate on the headway, or we can regulate on a time gap. So in this case now, I say that I try to keep delta t. I will come back to what delta t is, but I try to keep a time. And if I keep that time in a good way, I can get the completely swapped situation to the one I had before. So I can make sure that in space now, the disturbance is going to hit us at the same point. And that seems to be a good thing to do. So if we believe that that is a good thing to do, right, what is the consequences of that? And one very interesting consequence from a control architecture viewpoint is that keeping now such a fixed time gap between the vehicle is equivalent to saying that we should keep in space the same velocity. So it's like thinking about that we encode a reference velocity along the road, right? That's what I've written there. So what consequence does that have for a control objective? So instead of regulating one thing, we should regulate two things in hierarchy. We should make sure that every vehicle is able to keep that velocity over space. And then we should regulate their relative position according to this time gap. So it's a control architecture where we pull out the reference and let someone else decide that, and then we do this local regulation. And this now, of course, we can also motivate with some theory. We can put this in a framework, and here we put it, since string stability has been studied by so many, we develop a formalism on disturbance string stability. So what we have is that we have a number of vehicles now given by some dynamical control system which have some input disturbances. And then we say now that we would like these to be string stable in this sense. So it's kind of an input to state stability concept. So we say that we could have some initial condition and we have some disturbance, and we want the state of each vehicle to be bounded by these for all the vehicles in the platoon. So this is a stability notion that we are using here. And what we want to, then we develop various type of control on top of this. So just give you one example here. So one thing that we can prove is that we can take this concept and make it local. So we can now prove that if it's so that I can keep every state here bounded by its own initial condition, what the vehicle in front is doing, and the disturbance. If I'm able to do that, so it's a local condition, then the whole platoon will be stable in that sense that I introduced before. Okay, so this seems to be fairly abstract, right? So can we actually come up with controllers that fulfills this? And we can. So let's look at one such controller. So in one case here, now what I do is that I introduce a quantity. I call it small delta I there. So this is a quantity that I would like to keep small. And you see that that depends now on the time gap that I have to the vehicle in front, plus an error term, and that error term is the velocity error. So I just weighted together now how well I'm able to keep the time gap with the error in the velocity, and that's what I'm controlling. And if I'm controlling that well, and that's what this theorem says, so if I'm able now to keep that delta small in that sense, then this is string stable in that sense that I introduced before. So let's try out that on the experiment now that you showed previously. So notice two things now. First, let's look down here to the left. So this looks a little bit more complicated before, but I only made two major changes. One thing is that I have introduced the road grade. So I say that I have a road database that tells me the road grade. So the top diagram there, I know that. I plug that into a new block I call platoon coordinator. The platoon coordinator computes the velocity, this vref that I told you before. The same velocity communicates that down to the vehicle controllers, and the vehicle controller execute that. So they control so that we try to keep close to that. And you see here, so these are hi-fi simulations with very detailed vehicle models. But you see in this case, it works very well. You see the velocity is changing, of course, because that it will do now with the formulation that I had. But all the vehicles are able to keep that velocity, which in this plot is defined over space. Right? So over time, they are going to change, of course. And also notice that the distance between the vehicles is going to change. They will vary a little bit. But they vary for us here to benefit the fuel consumption. So this is the way we choose to do the control in this layered way. Notice now that I didn't say where do we compute, who compute this platoon coordinator. Should that be done in the first vehicle or in all vehicles, or should it be done in the infrastructure? This is one thing that we are working now on very much so, that we try to move this out and put this in the cellular network. So if we think now that we have a cellular network, or if you are into cloud computing, you call this now the edge cloud or the fog, right? So you can now think about controlling this process from basically from the base station, and that you now move that control process with the mobile vehicles here and do that control in this way. Interesting also from a communication viewpoint is that this requires now some changes to how the mobile system works. Because remember, when even if me and Professor Cheng sits in the same car with our mobiles, the handover when we move from one base station to another base station is not synchronized. It could be so that your mobile changed before mine, and so on. You remember that you measure more or less the quality to the base station, and this is an independent process. Imagine now that you have 3 vehicles that you want to move together, and they are connected to the base station. It's more or less like you have 3 different mobiles. Or you have 6 if you have both both transmitters and receivers. So this wouldn't work, right? If you don't coordinate it, you want to have a process where they move synchronously now, right? Because we talk that we are moving the control from one base station over to another one. So that needs to be following in a synchronized way. So that requires now some changes to how handover is done and so on. And we have developed some of this together with people working on this at Ericsson. Okay, so this was a little bit on the lower level, on the vehicle platooning. Let's now move up and let's think about how we should form platoons. How do we form them online? And the way we are doing this is very much built, you can say, on top of what you see before. So let's say that we have vehicles coming from different directions. They are sharing a segment, and then they are splitting again. So the way they are being formed, the platoon now, is that we have control of these vehicles from the infrastructure, as you see in this picture. And then from the infrastructure, you compute reference velocity, just like you have seen before. And this reference velocity is now generated in the infrastructure and communicated down to the individual vehicles in this way, right? The difference now is that we need to take into account traffic here. Because if there is a lot of traffic around, of course, you need to handle what velocity you will be able to keep in order to form that platoon. So this understanding of this problem led us to try to understand better under what circumstances could one form platoons. And as always, I think it's good to sometimes go to some experiments and see how this works. So what you see here is experiments that we did also outside Stockholm, a highway segment that you see down there, just 10 kilometers or so. And we went, try to form this platoon over and over again. And we are sitting in these videos, we are sitting in the second vehicle that tried to merge with a vehicle in front of us here. And this was done 600 such test runs. I was not driving the vehicle. But anyhow, it was over a month or so. Notice that now and then we are passing these gates there. So these gates are these type of things where you have sensors that sense the flow, the velocity, and the density of vehicles. So out of this information, we can either analyze data and get, so to say, a steady state situation of traffic And this is what one in traffic theory is called the fundamental diagram. So here you have the density of vehicle on the x-axis, and on the y-axis we have the velocity or traffic flow. So you see that if we have a low density, we get a linear increase of the traffic flow, which is what everyone, so to say, expect. Then at some point, you come to the limit where the road is not going to able to handle more vehicle, right? And you get the saturation and you get congestion. So out of this now, we can analyze how are we able to actually form platoons, or how can we control platoons so they are being formed under these circumstances. And for instance, we analyze different situations and how long it will take to merge and so on, and how we can predict that thing. I would like to talk a little bit about an exception now. So in this experiment, sometimes this situation happened. You see that we try to form a platoon with the vehicle in front there, but there is a red car there. So there is someone, of course in general, as you see in this picture down here, right? The trucks are supposed to drive slower. They typically drive 85 in Sweden, and the other one, cars, drives 110 kilometers or so. So they will pass, right? But in some situation, this happens. So we call this a persistent driver phenomena. So we have this fact that actually the human who was there didn't behave in the way you would expect the human to behave. And it happens sufficiently often to think about how can we predict driver's behavior, the human driver's behavior, and handle that in this type of situation. Of course, yet I don't think anyone in this about automating vehicle have a solution to this problem of how to handle the human drivers. But at least it's important to think about it, how to do that. Okay, let's go to the last part, and that's the highest level that I would like to very briefly talk a little bit about. So how do we coordinate large fleet? And large fleet, I'm talking about over the whole of Europe, like I said in the very beginning. So one thing that we have developed there is a very pragmatic way of solving this matchmaking problem. So what is default information that each vehicle here would have is that you would know what is your most efficient route to destination. So how should you drive? Everyone would know that from the start, right? And if you know that, what you then could be doing is that you then adjust a little bit your velocity so that you maximize the amount of platooning going on here. So you solve an optimization problem, which is basically a time scheduling problem. We don't allow to stop any vehicles or so, but we just adjust a little bit the velocity, some kilometer per hour or so. Changes that the drivers here wouldn't notice that they do, but that would maximize this type of platooning. So this we have studied both in big numerical studies, but also we implemented something like that and run over Europe with vehicles going from Sweden or Stockholm all the way down to Spain and so. Not with very many vehicles, but just to see that the concept works. It's also interesting to think about if we now coordinate a whole system like this, how does it scale? And how large implementation of this do we have to do in order for it to benefit? So we have run some study. Again, this is back to the German highway network. So how large penetration? I said earlier that there is 400,000 trucks basically running around there. Do we have to implement this in half of them, or how many? And this one can easily study by numerically estimating how much traffic assignment that is going between different areas. And this is what you see here. So we have fuel savings on the y-axis. So it saturates at about 10% here. And you see that already with a few thousand vehicles, we reach more or less the saturation. So this suggests then that it's enough to have a penetration rate of less than a percent. And we will then be able to or a few percent, and we will then be able to handle this situation. The last thing before the conclusion, I just want to show you something very recent here that we start to study. So when we have what I call here massive track platooning, so when we will see these platoons all over on the highway, how will they influence the rest of the highway traffic? right? Of course, there is a difference when you drive, like in this video, when we drive this platoon together like that, or if they go individually. But could we try to have some theoretical understanding of that, of this consequence? Is it good or is it bad or so? It would be nice, right? And we have made some first attempt to this problem. So we try to model now traffic congestion, basically having a queuing model where we represent the scenario that you see here. So the red vehicles are now going in platoons, and the blue are just the rest of the traffic. And then we wonder now, so for instance, if more of the red ones are, if we have the fraction in total of vehicles, if more of the fraction is red ones, what is the consequence of that? And the other thing is, so if these red ones go close together, or the inter-vehicle distance is larger, what is the consequence of that? And with this fluid queue model that we have considered, we get results which is like this. So as the fraction of vehicle increase, of platooning vehicle increases, the average queue length, so the congestion, is decreasing. And there's even a magic number here where we get down to no congestion at all. And the same thing now if we let the average length between the distance between the vehicle go down, it's the same thing, that it's the overall performance of the highway is getting better and better. I won't have time to go into detail of this particular model that we developed. But anyhow, if you want to speculate about what implication this might have, so if you think back of that picture of the control of automated vehicle from the infrastructure, we can now think about how we could, instead of just minimizing the fuel, so to say, having which is like a local optimization, right? Where we can think about a more social optimum here. So could we optimize what a highway during different time of the day is able to capture? So how we optimize this infrastructure to serve as good as possible the vehicles that we are driving there. Okay, so with that, I would like to come to the conclusion. I hope that you agree that actually this type of problem, which I call cooperative road freight transport, is a great problem. There is a lot of networking, control, communication, and sensing and so on in this problem. It's also so that it's quite nice and to open up also with the possibility to connect these different layers. Also scientifically, if you think about it, we are talking at the highest level is logistics and operational research. Lowest level is maybe mechanical engineering or so, right? But in what I describe here, it's really a capability to connect there, where the connection is information and communication technology and systems and control coming in, right? There are many more things, so if you gave me another hour, I would be happy to talk about them, but I will just mention it here so we can open up for discussion. One thing is, what's the cost here? And what should we optimize? I said this about global and local objectives. So think about now, should each driver, each vehicle get paid depending on where they drive in the platoon or so? Or should we have it as a service so that you pay and then you can go in this platoon? And so what should it look like? And if you think about from a fleet owner perspective, how should that market look like? And just to see that this is non-trivial, if you have many vehicles, so if you are DHL, for instance, or you just have 5 vehicles, the one with many vehicles benefit the others, right? Because you provide opportunities for platooning. So you might not want to give up that to the others, right? So you have an asymmetric market, which is quite interesting to study here. More from an information viewpoint, in the last part here, I talked about it as if all this information about who goes where is available. But how do we make that information available? And how do we share it here in a suitable way? And of course, in general, the fleet owner and the businesses here, or the one who owns the supply chain, they don't want to post this on Facebook, this information, because this is business information. But what we have shown is that some of this matchmaking one can actually do in a private way. So I put here, it says privacy filter. So one can do some of these things using under encrypted data. And I mentioned also this thing about the human decisions. It's not at all just we in Sweden who are doing these things. There's quite a lot of activity. So in Europe, all the 6 big track manufacturers are involved in this. And we are just now negotiating a new big EU project that is just going to start, where there will be multi-brand platooning. So far, there was no Scania going with a Volvo or a Mercedes going with a DAF or anything like that. They always the same vehicles. How will this work when you have different vehicles and so on? That I think would be very interesting to see. Okay, so with that I would like to thank you so much for your attention. So thank you.
Thank you. Now we have Q&A.
Yeah, thanks for the very clear and nice talk. Thank you. Thanks for the very nice and clear talk. Just have perhaps the one question and one, let's say, thinking aloud, okay, idea. One is that the question I have is that it seems that if you do platooning, the first vehicle is still taking a lot of this air pressure, so his fuel saving may not be as significant as the second and third one. So if they are from different company, how would they actually share the cost saving? Because I may not want to share my cost saving with you. Maybe this is because you need them to frequently switching who is taking the lead so they can even things out. This is first question maybe. Second is seems the first guy is taking the air pressure. I was wondering whether or not some like Uber, like local vehicle can come into the play. Like let's say I need to travel between 2 cities anyway, so I'm driving a car. So I can maybe receive some job information from an Uber-like platform. And if I take the job, that means I want to take the lead. Maybe I'm driving a small vehicle, may not like a truck, but maybe they also take away some of the air pressure of the trucks behind me. So that way I take care of the leading position of this platooning. At the end, I get some reward, like playing from the Uber platform. I was wondering if...
Thanks, very nice question. So let me start with the second one. So, and actually let me point out that when I was here three years ago, I checked online and I saw that in Hong Kong, there is like a Uber service for goods. So I don't know if it's alive any longer, but you could actually say that I want 5 tons from this position in Hong Kong to another position in Hong Kong. And so what you say there, I think that this opens up to some sort of sharing, which we maybe don't know exactly today how it's going to happen. I think it's a little bit more complicated than it might look first, because for one's sake, you know, these vehicles, as you saw in all experiments we do, they look quite similar. And I think that you would assume that they have to be quite similar. Of course, that similar needs to be defined, and I think to make it easy, it will first be that they are maybe exactly the same or so, right? Like what I showed you here. And the reason is that it's very hard to predict, because, you know, this area of the fluid dynamics and so on, it's very complicated phenomena that can happen when you have different types of shapes and so on. So I think this is what one would expect, that not very big changes between the vehicle to benefit from that. So I'm not sure if we will see, so to say, special vehicles being the front runner. I think instead there are other solutions. We actually wrote something about what you explained about that you would shift the front runner, right, the lead vehicle, a little bit like you see bicycling race they do, right, that you shift. The thing is that in practice, this is not so realistic, because in Sweden we have mostly two-lane highways, right? So even if you have 3-lane highway and you want one vehicle to pass another one, right, and you do that often, it screws up a lot of traffic. So I think instead what you will see is maybe that you will handle, so to say, the benefits in some other way. And that could be what I mentioned when we talk about the pricing here. You could say that maybe the first vehicle is getting paid somehow for driving first for some distance. Or maybe after a break you will shift and so on. I think that we can, so to say, from an academic viewpoint, think about all kind of solutions to this problem. And then what is going to be implemented in the end is probably something which is simple enough so that you can handle it. But it's a good point, that the benefits, mapping the benefits to how much you pay or so, it's not obvious, right? Also, if you have different masses of the vehicle, if you have a heavy vehicle here, you maybe benefit more. So how should we handle this? You know, should you pay more and so on? So, yeah, that's a good point, right?
I'm just curious. I'm not from this field, but no. I'm just curious why they design trucks like building.
Oh, yeah.
Straight instead of more like an airplane.
Yeah. I was also, you know, like some 15 years, but as I said, I mean, I didn't do my PhD. I'm a control theory guy. When I started to work at this, I asked myself the very same question. Because as you know, in US, right, you have, it looks like this, right? They have the front like this.
But all, everywhere.
No. In US, they don't look like this. In US, you have a front which goes like that, right? So the reason is, how do you define the legal length of the vehicle? Right? And here in Europe, at least, we defined it from the front there. So therefore, you want to make the front as little as possible because you want to maximize the length there. In US, it's defined by where the driver is sitting. So then it's perfectly fine to add something. Because otherwise, if you could add something here, of course, you will make it drop-shaped or something like that, right? But that's the reason. So of course, in all this business, you try to maximize the volume that you can carry here. Because, you know, thank you. That's a very good question.
But you can save energy, of course, if you build some this way.
Yeah, but if you would add now, so if you build something like this, so you would add 5 meters, then legally you need to shorten what you can carry here by 5 meters, because you have a fixed length of the vehicle.
What you're allowed to carry.
Exactly. There is a.
You can change the law, right?
Yeah.
So it's a public policy issue.
Yeah. But this is regulated in. I'm sure it's regulated in Hong Kong also, because you know you have to drive over bridges and all this things. So there is you know, the total mass and the length and all these things is. But to mention something related to this, which I got a little bit into, is actually this policy. How you set this policy, because these vehicles are now something we can call semi-automated, right? They're not fully automated, but semi-automated. So is it legal to do what I showed you here? So how close can you drive? What is legal? And the interesting thing is, in Sweden, what I showed you is legal, as long as the police who stand on the side of the road says that it's legal. While when you drive in Germany, for instance, they have a minimum distance. So it's different than in Hong Kong. I don't know what is the rule, but anyhow, so you see that one needs to handle these things as well. Yes. Yeah.
So, also a question. For the first vehicle, do I lose anything if I, serve as the first one, leader, instead of Johnny and gain benefit?
Yeah.
Yeah. Okay. Then if I do not lose anything, then if you post this from a game theoretical viewpoint, and then if I join it, then I gain things. If I serve as the first leader, I do not lose anything. Then in any case, I would just play the game, right?
Yes.
So
so answer to the first one, you who were careful and saw my air drag, saw that actually the first vehicle was in there, and it's actually benefited. If it's close enough, you benefit a little bit being in the first compared to not being in the platoon.
Yeah. But then the pricing thing, all the social thing, then that's not a problem, right? Because then everybody should be willing. So, of course, there's the privacy there, right?
I'm not saying that it's a problem, but you get different benefits, right? If you buy a service, otherwise we maybe pay the same price if we get the same service. Here it depends on what type of vehicle we are and where we are, right? How much we benefit. You see, so it's not so easy to say offline what benefit it would be for me to go behind you if we go a long distance. So this game that you formulate there, it's a very interesting one, but it's also very interesting to say, how is that going to be solved? Is that going to be solved by me monitoring my consumption and then say that, okay, this is what I benefit in general, and therefore I'm willing to pay this or be part of this in that way? Or should there be a system that is monitoring this and you have to publish how much fuel you are consuming? Do you see that this is an very interesting systems theoretic question to try to understand what is good. And you also want a market now which is fair, right? So, thanks.
It's human. Yeah. Because like somebody's taking advantage of you. So, yeah. Yes.
So conceptually, why is it so difficult to consider the mixing of the multi-brand?
Yeah, thank you. That's it. So, and actually here, unfortunately, it's not so good quality. But actually, in this Scania platoon, there is a Mercedes going in the end. So even Scania owns Mercedes. That's right. So why is this so? Because in all the control I showed you here, that is developed model based, right? You saw I showed the models and so on. So I assume that is known. That also means that I have to know something about the drivetrain. I need to know something about the control algorithm that is, for instance, regulating the gear shift and so on. This information you don't want to tell others because this is a sales argument, right? How well you are actually running your track. So when you now come to that level where you say that, okay, we need to exchange some information because when we are going in a platoon like this, you can imagine if this truck is not loaded, it weighs maybe 3 tons, or if it's fully loaded and weighs 40 tons, there is a difference, right? The control system is different. So one information that you want to exchange is a mass. But then let's say that this truck has terrible brakings. This guy didn't serve his brakes. Then maybe he would like to know that, right? And you can add to this thing, right? So you see that you would like to have full knowledge of everyone on, but when we give up and say that we have multi-brand platooning, it's less clear what is that information without giving up, so to say, information that you from business perspective don't want to give up. So what we try now is that we try to formulate control problem where you can say that you want to do the design here with certain information and be able to specify how does this information relates to the performance. So relating to some of your work, you could formulate it to a robust control problem, right? By being specific now and say that this and this information, but maybe this and these parameters are less important, and be able to specify that. That's a.
So it's really because of very high level of uncertainty, real heterogeneous.
Yeah. So if you allow high uncertainty, so for instance, say that you don't tell the mass, then you have huge uncertainty, and then what would that mean? It would mean that you have to drive with large distance between the vehicles. And that will transfer into that you won't benefit that much. So you can say that you have like a business case here now, which is, to me, it's completely new, where you get this type of performance trade-off from somehow some sort of privacy issue about what you should give up about your models in the system. Thank you, thanks.
I got 2 questions. The first one is that when you talk about cellular signal tower and then communication between. Okay. So the first question is about that when you're talking about cellular signal tower and then the communication between trucks, is it 2 systems? So like because sometimes we know that sometimes signal tower may be failing. So how do you continue to have this to continue to work? And my other question is, could this kind of system seems to solve many problems? Can it use in other like air trafficking or like in biological system, because they are also networks? But I feel like it's kind of suitable in some sense, like drug delivery sometimes, so you're not going to some network and then divide. Is it possible to use this system as well?
Yeah. Thank you very much for those questions. So if we start with the last one again, so this thing with having a networked system, what we say, systems which are interacting over networks, that is a lot of theory going into that now, trying to investigate. And there have been quite some discoveries about that. For instance, you mentioned in nature, right? That in nature, sometimes communication between different entities done in a very efficient way, or control is done in an efficient way. And in some engineered system, we try to mimic how this is happening, right? And how you could do that. And while talking about that, I lost your first question. Your first question was on.
The first question is about cellular tower. And
yeah, very good. Yeah. So the experiment you saw here, there are these are vehicle-to-vehicle communication. So basically, you have an antenna there, or actually in the more modern one, you have antenna now built into the rear view mirrors, and that is using the communication the Wi-Fi communication protocol. It's called 802.11p, and this is terrible. It's very bad, and for those of you who knows a little bit about communication and control, know that the worst thing you can do is to do broadcasting when you want to close the loop, right? Because broadcasting means that you just shout out what you want to communicate, and then no one else can communicate while you are talking. While here, I talk about situations where we actually would like to communicate in an orderly fashion from one vehicle to another one. So Wi-Fi is not very good, but it's a standard there and so on, something that we have to live with. I think in the future it's going to change how we communicate between vehicles. If you go to what I showed you about the vehicle to infrastructure, what I would then talk about is that we have a regular base station here along the road, and that we now communicate over 3G, 4G, or 5G to that base station and then down again. And maybe you do some communication in the base station, or you do communication close to the base station, so in a cloud which sits on the cellular network. And again, in the future, when we are running these systems commercially, I believe that you will have multiple type of communication modes. So I think that we will both see that type of communication and the communication between vehicles. And there's also other means you can communicate. There are also within sight type of communication that you can have between vehicles and so on. And I think the issue is not to rely on just one type of communication, because you have this uncertainty there. So, thank you. Thanks.
Maybe a follow-up question. Let's say now it seems that some company like Amazon is using UAV for delivering goods. So you can imagine the UAV can also do platooning, but I was wondering what's your opinion upon doing platooning for UAV system, and what would be the new challenge, or what would be the similar challenges?
I think, yeah, if we think in general about how we are running this transport system, we can go to, I mean, the most organized thing is to be on rail, right? That is efficient and so on, and we know what is going to happen, because most of the time we really follow the rail and trains and so on. Going on road is quite organized also, right? We know where the roads are. We can choose which road to take and so on. And then we can go up and being more flexible, right? And if we look at the regular air traffic today, right, it's quite organized. We have to follow a certain path. And of course, there is a discussion about free flight and so on, but it's not to a large extent implemented. You're following. So, of course, when something like drones comes, it's completely open. And you fly everywhere, and then now we have all different discussion again about regulations and so on, where you should be allowed to fly and so on. In that area, there is quite some discussion about creating zones or highways in the sky. I know, for instance, in the Bay Area, they have some work on that, where they say that now we should go in some orderly fashion with these drones, and maybe then also go together, because if you meet and so on, it's easier if you go in this type of platoon. So I think it's an interesting question from the viewpoint of how do we organize system? When do we let system organize themselves? And when do we provide some sort of restriction, or if we talk like engineers, some sort of architecture? And many of the success stories, so again, if we talk about our internet or mobile communication system, one reason for the success is that it's been very well structured and organized, right? That has allowed us to develop it so fast and good. And I think that some of this new technology we will also see. So personally, for instance, I believe that we would not see completely self-driven vehicles. I think that all vehicles that's going to run there will be connected in the future, because it's so clear that it's such a benefit to actually have some sort of coordination over vehicles and so, and probably also when it comes to the drones there.
Yeah, I wanted to ask about the automatic drivers, which is, I know, a possibility, especially right now they're doing some testing with self-driving cars in Sweden in particular. So I was curious, is this something that this sort of freight transport system is heading towards? And if it is, then how is it going to look like?
Yeah.
And this is the first mini question. And the second, I wanted to ask, what is the possibility, the business possibility for companies that are not related to freight transport directly in this? Could it be potentially that cars that are passenger cars run like this in the future?
Yeah, yeah.
Thank you.
For the first question, it's also related. It was nice that you know about this Drive Me project by Volvo. So Volvo is putting 100 vehicles with some self-driving functionality out in Gothenburg to ordinary people who use them to drive to work, and they automate while they go on the highway. And I think that shows a little bit a more traditional, vehicle manufacturer attitude to self-driving. You think that, okay, while they go on highway, that is a fairly organized environment or so that you can handle that. I didn't see much from Volvo where you go completely out, so to say, downtown in the most complicated situations. And I believe that also here, what I think you will see, if this technology take off here, that you maybe will see that there will be dedicated lanes in the beginning for this. So, or I mean, this might be dynamic dedicated lanes, right? So during certain time period, when there is not any other traffic, it's rather simple to solve this. The hard problems, like what I showed here with that type of white car, right? If we have a lot of white cars around you driving downtown Hong Kong here, I mean, it will be a very, very hard problem. And I think it takes a long time until we are able to solve that type of problem. So I think we will see solutions where we solve the easy one. And actually, some of the business cases, since you talk about business here, is areas like up in the very north of Sweden. There we have mines, and there are a lot of transport going with these mines. The same thing is in Australia, in the central of Australia, right? Long transportation and so on, not many cars, where it's easy to solve this. When it comes to other businesses, I think this is also a very, very interesting thing to think about. So if you believe in that thing about a platooning service, and so who is going to take that? And as I mentioned, we talked about Peloton before. Peloton have their own system. They call some sort of a network service provider, something that just handles within your own trucks that you now own, that you could run. Something like that. All the big truck have their own fleet management system. But then, of course, if you go to DHL or Schenker or some of the big ones there, they have their system, their logistics system. And then, of course, we have all the data companies now, right, who could provide this service. And who is interesting? The only thing I can say from my research perspective is there is a lot of interest now in that. In this, and I've been contacted with a number of different very big and small companies that see, so to say, do a little bit these calculations to see the opportunities. When I speak with Volvo and Scania, I think they don't know yet. I mean, they don't jump in and create this big service because they don't know if that is something they're going to make money on or how it will look like. And also their customer are the logistic companies. And in a sense, you can say that if this would create an open new market, you are killing these logistic companies, right? It's a little bit like what happened with Uber and Uber killing the taxi companies. And of course, if you're now selling trucks, you don't want to tell those who are your customers that maybe in future we won't have you any longer because we will run this in a more distributed way.
Follow up in China, could the governments actually be the ones who would fund this system because of the environmental aspect that you talked about. So basically there could be anyone who invests in this, it is that beneficial.
Yeah, not only in China. I mean, we have this very same discussions in Europe and in Sweden. So, I mean, should every country have their traffic authorities that handles the roads and so on? Should this be a service you get from the traffic authority?
But in that case, how would the sort of logistics companies work? They would just eradicate, as you said.
Yeah. But I think I mean, the way, again, in some of these projects we have in Sweden, we work with academia, industry, and authorities. And very close together because we talk about the law, right? The government need to change things, and they are the one who decide, even if new technology come up. And also these business cases are a little bit unclear because we talked about if this is legal or not. I mean, the company maybe hesitate to develop some of these business cases if they are not clear if it will be legal. So I think there is a lot of open questions around that, which are still also research questions. And we try to understand a little bit some of the fundamental issues so I can say that this is probably a stupid idea to do or this is not. So one understand what consequences that would have.
Okay, thank you.
Thanks.
Yes.
Yeah, well, one legal question, if you have a completely autonomous vehicles, not now, maybe 20 years or whatever,
Yeah.
You must change the law, because I think the law today say a driver must drive the car.
Yeah.
So that's, and regarding the question of AUV, is that, well, they don't need to look like houses. So they can look more like fish, so they don't have the problem of,
Yeah.
right? So they don't need the tuning.
Yeah, but I think a problem there. Notice that freight, transportation in the air is a very small percentage of all transportation.
So
It's
they
very,
don't cost that much.
it's very costly. So I think also the one who work with the drones, right? You don't expect that that's going to take over all the bulk transportation. I mean, if you can't transport on water, you do that, right? And big ships. If you have to go over land, you probably, a little bit you do on rail, but most of that is in this. So I think that we won't see any big, I think the last mile is kind of what this Amazon and others are looking into, right? How do you get out to the customer? Today you have to drive all this logistics and so on, which might be very costly. When it comes to the legal, some things are happening. So this experiment that was mentioned here that Volvo is doing with autonomous vehicle. So now it's actually, since last year, it's legal in Sweden to do this type of experiments. And that, of course, had to happen because Volvo had this. so we were a group who went together and lobbying for this and so on. And it was a lot of power from the industry there to do that. It's not legal to have such a system running as a commercial system. But I guess that you will see that soon. It will probably not be what they call SAE level 5, not fully autonomous, right? But it will be with some more automation. I think we will see that fairly soon. I think. And at least in the European Union, what is happening with that respect is that some countries want to be front runners. It's a bit like in US where you see the different states. They want to be the state which is like Nevada and Arizona and so on. We want to push this. And you see that in Europe. So in Europe, I think it's, Netherlands has been one such country. Sweden also tried to, push these things. And Germany with all their industry will also be pushing. Yeah.
I think the very original motivation for vehicle platooning is really to solve the traffic congestion issue, right? So for drones, it's not an issue yet.
Yeah.
You have all this open space.
Yeah, but what could be interesting is to, you could benefit if you form. Let's say that you decide now to go with 5 drones, or go with them in some, you can go with them in a formation, and then you could reduce the. I guess that's it would be an idea.
Different performance.
Yeah.
You can have like 10 drones cooperating to have the same heavy load.
Yeah. But notice here also when we talk about this thing about the infrastructure, you can say that, the road infrastructure is used in a particular way today for a very specific historical reason, right? And what is happening now is that is shifting completely thanks to the type of technology that we are working on, right? And I think that there is much more now, and it will probably be more in the future also, about where you connect the development of this infrastructure to something which is actually more sustainable and beneficial for society. So if you take the area of urban planning, that is changing completely. We have new regions in Stockholm. I know they build without parking places and so on because they expect that people will not own a car, because they will have these self-driving cars that come and pick them up and so on. So this is changing, that you can now use space for other things than just for parking houses and so on. But of course, it will take some time. Yeah.
Very interesting, huh? Yeah. But I think probably we can now apply this in Hong Kong, because the road conditions up and here and turnings is a very complete situation. Yeah, but in country with a flat lane, without up here, down here, I think it's much better. Yeah. Yeah. So let's give a warm applause to Professor Johansson. Right. Thank you very much.
Thank you.
So we have small.